So, if we go back to 2013, there's a perfectly healthy woman who, walked into a hospital in Los Angeles, went under general anesthesia, and just had her breasts surgically removed.
Right, yeah.
And the crazy thing is, she wasn't sick at all. Like, there were no tumors, no jagged white line on an X-ray to point at and say, there's the problem. But there was this hidden typo in her DNA that essentially told her she was a ticking time bomb.
Yeah. And that moment, I mean, it completely shattered how we think about a medical diagnosis because we are so used to reactionary medicine, right? Like
Yeah.
waiting for something to break and then trying to fix it.
Exactly, yeah.
But this was something entirely different.
Which is exactly what we're doing a deep dive into today. We are looking at this fascinating and honestly sometimes murky world of genetics using Dr. Daniel Wallerstorfer's book, Unlock Your Genes for Precision Health.
It's such a great source for this.
It really is. We're going to unpack the exact biological mechanics behind cancer, how this one high-profile preventive surgery just changed the world, and why your DNA isn't like some crystal ball predicting unavoidable doom. It's actually a personalized instruction manual for your body.
Yeah, and to really understand that manual, we kind of have to start with the moment that shifted the whole cultural conversation around genetic testing.
Angelina Jolie surgery.
Right, exactly. April 27, 2013. Angelina Jolie waking up at the Pink Lotus Breast Center after a double mastectomy.
So she makes this massive, totally irreversible choice while perfectly healthy. And you read about her family history in the book, and it's just, I mean, it's a devastating shadow to live under.
Oh, absolutely.
Her mother fought an 8-year battle with ovarian cancer before she passed away. And then, she lost a cousin, a great aunt, and an aunt, all to breast cancer.
Yeah, it was everywhere in her family tree.
Right. And her grandfather died of sweat gland cancer, and her uncle died of prostate cancer.
Mm.
That is just so much trauma. But what kind of absolute certainty did a genetic test actually give her to justify removing her breasts?
Well, the test showed she had inherited a mutation, like a specific defect in a gene called BRCA1. And the numbers attached to a defective BRCA1 gene are just incredibly sobering.
Like, how bad are we talking?
Someone with this defect carries an 87% chance of developing breast cancer. And the majority of those cases strike before the woman even turns 45.
87%. Wow. That's not just a slight increase. That's like almost an inevitability.
It really is.
Yeah.
And on top of that, it raises the risk of developing ovarian cancer from the average, which is about 1%, all the way up to 40%.
Oh, wow.
Yeah, so she was looking at these staggering odds. And by undergoing the double mastectomy, removing most of that breast tissue, she dropped her breast cancer risk all the way down to about 5%.
Which is actually lower than the average 12% risk for a woman who doesn't even have the genetic defect, right?
Precisely. She took control of the odds, and she wasn't alone in this. While she brought it to the global stage, other public figures were dealing with the same inherited defect.
Right. I think Christina Applegate was one of them.
Yeah, she had opted for the procedure back in 2008. And the Osborne family was deeply affected too. Sharon Osborne underwent the surgery, and her daughter Kelly, who also carries the faulty gene, has publicly stated she plans to have the surgery after having children.
And Jolie didn't just stop at the mastectomy, right? Because
Yeah.
you mentioned that ovarian cancer risk jumping to 40%.
Yeah, she didn't stop there. 7 out of 10 carriers of the BRCA1 defect actually decide to play it safe and remove both their breast tissue and their ovaries. Jolie had her ovaries and fallopian tubes removed at age 39.
Which, if I recall from Wallerstorfer's book, is the exact age her mother developed the disease.
That's right.
But how do they even monitor for that? Because ovarian cancer is notoriously hard to catch early.
Oh, very hard. It's mostly silent. Jolie made her decision after a specific blood test. It's called a CA-125 test. Came back with concerning values.
What is that exactly?
Think of CA-125 as like a sort of chemical smoke alarm in the blood. It's a protein that can be shed by tumor cells. Now, it's not a perfect test, but it was enough of a warning sign for her.
Yeah, you wouldn't want to risk it.
Definitely not, because the brutal reality of ovarian cancer is that in about 1 in 10 preventive surgeries, where they are just taking the ovaries out to be safe doctors, actually discover a previously undetected cancer already growing.
That is absolutely
Yeah.
terrifying. But removing ovaries at 39, doesn't that plunge a woman into immediate menopause?
It does, yeah,
Yeah.
because you're taking away the body's primary source of essential hormones like estrogen. So because of that severe biological impact, doctors usually recommend waiting to do the procedure between the ages of 35 and 40, assuming the woman has already had the children she wants.
Right, that makes sense. The cultural ripple effect of Jolie publishing her article, My Medical Choice, in the New York Times is just mind-blowing to me.
Oh, it was huge, the Angelina effect.
Yeah. The book notes that requests for BRCA1 analysis spiked by 64% within 2 weeks. And today, around 100,000 women in the U.S. undergo this preventive procedure every year. And it even caused, like, a legal earthquake regarding who owns our DNA.
Yeah, that is honestly one of the most fascinating side effects of this whole story. For 20 years, companies could actually hold patents on human genes.
Wait, really? Patents on human DNA?
Yeah, if a company patented the BRCA1 gene, nobody else was legally allowed to run an analysis on it. It was this incredibly lucrative monopoly.
Until the public sensitization led activists to protest all that.
Exactly, culminating on June 13, 2013, when the U.S. Supreme Court finally ruled that human genes are a product of nature. The ruling was basically, you can't invent them, so you can't patent them. Yeah, and in a single ruling, the patents on over 4,300 human genes became completely void, which just opened the door for widespread affordable genetic testing.
It's amazing how one person's story shifted public health and the law so drastically. But mechanically, I keep getting hung up on the biology of it.
Yeah.
Like, how does one single microscopic typo in your DNA wield enough power to cause such devastation across entirely different organs like breasts and ovaries?
So to understand what is actually happening at a cellular level, we have to look backward, like way backward in evolutionary history, down to the simplest organisms on Earth, unicellular bacteria.
Okay, bacteria. Why are we talking about bacteria when we're trying to understand human cancer?
Because, well, a bacterium has this one incredibly simple primal survival strategy. Divide into two cells as fast as physically possible.
Right.
The faster they divide, the higher their chance of survival. Over millions of years, evolution optimized this rapid-fire division using what we call growth-animating genes. They are basically biologically hardwired to just hit the gas pedal and multiply.
But humans aren't unicellular. I mean, we have trillions of cells. If our cells acted like that, we'd be in serious trouble. Like, imagine if your bone cells just kept dividing rapidly like bacteria. You wouldn't have a functional skeleton. You'd just be, I don't know, a shapeless, expanding lump of bone tissue pushing in every direction.
That is a brilliant way to visualize it, honestly. When multicellular life emerged, cells had to learn teamwork. Some cells formed lungs, others formed bones, but to maintain those complex structures, the organism needed a control system.
Okay.
We actually still have those primitive growth-animating genes inside us. We call them proto-oncogenes, or gas pedal genes, and they initiate the necessary cell division when we need to, say, heal a cut or grow hair.
So to stop us from becoming that shapeless lump, we needed some sort of brakes.
Exactly. Evolution developed tumor suppressor genes, brake genes. When a cell needs to divide, the gas pedals activate. When it's time to stop, the brake genes step in and halt the division. It is this beautifully balanced microscopic tug of war.
So where does BRCA1 fit into that tug of war? Is it like a brake and gas pedal?
Actually, BRCA1 is one of your most important brake genes, specifically for regulating growth in breast and ovarian tissue. If you inherit a defective BRCA1 gene, its function as a growth inhibitor is severely weakened. It's essentially like driving a sports car with worn-out brake pads.
They might work for a little while, but eventually you're going to crash.
Right. Over time, that weakened BRCA1 gene randomly fails completely in a single solitary cell. And once those brakes give out, the gas pedals just take over without any resistance.
Oh, man.
Yeah, that single cell forgets it's part of a human being and reverts to that primal bacterial mode. It goes into overdrive. One cell divides into two, two into four, four into eight, compounding at a rapid, unchecked rate. And that mass of runaway cells is a tumor.
Wallerstorfer mentions this system can break from the other direction too, right?
Yeah, it can, yeah. You might inherit a defect that doesn't destroy a brake gene, but instead supercharges a gas pedal gene. The biochemical signal telling the cell to divide becomes so overwhelmingly loud that even perfectly normal, healthy brakes, like a functional BRCA1 gene, they simply cannot clamp down hard enough to stop the growth.
Wow, that makes the mechanics of it so much clearer. But obviously, science hasn't just stopped at BRCA1. The book points out that while BRCA1 affects about 1 in 670 women and BRCA2 affects 1 in 2,000, modern technology has broadened the horizon significantly.
Oh, massively. We're no longer just looking at two genes. Comprehensive genetic panels now test for at least 10 other crucial genes names, like PALB2, BRD1, and TP53. These genes might be, less famous, but they play highly relevant roles in regulating cell growth and repairing DNA damage.
But here is the statistic from the book that completely stopped me in my tracks, though. With all this talk of genetic testing, Wallerstorfer points out that only 10% of all breast cancers are classified as strictly genetic.
Yeah, it's a massive paradigm shift in how we categorize the disease. In scientific terms, that 10% represents cancers that are monogenetic with high penetrance.
Which means,
That's just a fancy way of saying a defect in just one single powerful gene like BRCA1 is enough to drive the cancer all by itself.
okay, so what about the other 90% then?
The remaining 90% are classified as age-related or sporadic.
But wait, if they are sporadic, does that mean our DNA has nothing to do with that 90%? Like,
Yeah.
it's just bad luck?
Not at all. Genes still play a massive role in that 90%, but the mechanism is entirely different. Instead of one massive defect, it's about a combination of tiny, weak defects.
Okay.
Let's look at the FGFR2 gene as an example. If you have a defect in this gene, it only increases your lifetime risk of developing breast cancer by an average of 2.76%.
I mean, 2.76% sounds like a rounding error compared to the 87% risk of BRCA1.
It is incredibly small, but the catch is how common it is. Almost half the population is walking around with one defective copy of the FGFR2 gene.
Wow, really?
Yeah, and 17% of people have two defective copies. In fact, only 36% of the population has two normally functioning copies of this gene.
So it's basically a coin flip whether I have an error in this gene right now.
Pretty much. And that's just one gene. There are many other genes out there with these common weak defects genes with names like VDR, AQ24, and CASP8. What modern genetic studies have revealed is that these tiny risks add up. They compound.
So they sort of stack on top of each other.
Exactly. Sometimes they even interact and reinforce each other. Wallerstorfer notes that in a worst-case scenario, if you inherit a whole cluster of these weakly defective genes across your DNA, the overall probability of developing breast cancer can compound to almost 70%.
Okay, hold on. If my compounding risk hits 70% just based on a bunch of tiny genetic typos I was born with,
Yeah.
how is that any different from the 87% BRCA1 risk? It sounds like I'm just as doomed. Are we completely at the mercy of these stacked odds?
That is the pivotal question. Like, are we just waiting for fate to strike? And Wallerstorfer addresses this by breaking genetic risk down into three distinct buckets. Let's call them the fate bucket, the casino bucket, and the lifestyle bucket.
Okay.
Understanding which bucket a gene falls into changes everything about how you treat it.
All right, walk me through the buckets.
Sure. So the first is the fate bucket. These are group I genes where if you have the defect, there is almost 100% probability the disease will manifest.
Right.
The classic example is the CFTR gene in cystic fibrosis. That gene's job is to ensure lung mucus stays fluid and slippery. When it's defective, the mucus becomes thick and sticky, which inevitably leads to severe pneumonia and lung damage. There's no lifestyle change that stops that mechanism.
Pure biological fate. Got it. So it's the second bucket.
Group 2 is the casino bucket. This is the high-risk gene group where BRCA1 lives, the 87% risk. In this group, it's a game of biological roulette. The outcome is largely unaffected by how you live. You could have perfect nutrition, run marathons, manage your stress flawlessly, and it will not decisively reduce that 87% risk.
So preventive surgery really remains the only truly effective measure there.
Exactly. Which brings us back to Angelina Jolie, the extreme measure for the extreme risk.
Okay, so what is the third bucket? Because if my compounding risk is 70%, I really hope it's in bucket 3.
It is. Group 3 is the lifestyle bucket, or the moderate risk group. This is by far the largest category. This includes everyone who has those multiple compounding gene defects we just discussed. And here is the crucial difference. People in this third group can actively lower their risk through behavioral and environmental changes. You are not doomed. You can fight back.
But how? If the gene is literally broken, how does a lifestyle change fix it?
Well, let's use the VDR gene as our prime example here. Medical experts widely agree that a deficiency in vitamin D3 contributes to the development of breast cancer.
Right.
So women are advised to ensure they get sufficient intake. The standard recommendation is about 20 micrograms per day to activate protective processes in their cells. You usually get D3 from sunlight, specifically UVB radiation hitting your skin, or from your diet, relying on stored reserves during the winter months.
So vitamin D3 is basically like a chemical key floating through the bloodstream, just looking to unlock those healthy protective processes inside the cell.
That's a perfect analogy, but, a key needs a lock. The VDR gene provides your body with the exact biological instructions to build that lock. what we call a vitamin D receptor on the surface of the cell.
Okay.
When the VDR gene works perfectly, it builds a perfect lock. The vitamin D3 floats by, docks flawlessly into the receptor, turns the key, and activates the healthy processes.
But the book notes that 1 in 8 people have 2 defective EDR genes. So what happens to their locks?
The instruction manual is flawed, so the locks are built malformed. The receptors are the wrong shape. The vitamin D3 molecules are still floating through the bloodstream, but they can't dock properly into these misshapen locks.
Oh, I see.
Because of this, the healthy processes are only weakly activated. And Wallerstorfer points out that this weak activation increases a woman's risk of developing breast cancer by an average of 6.8%. It also plays a relevant role in the development of osteoporosis, and in men, it raises the risk of prostate cancer.
So if I'm one of those 1 in 8 people and my receptors are structurally malformed, what am I supposed to do? Like, I can't rewrite my DNA to fix the lock.
You don't need to fix the lock, you just overwhelm the system with keys. The solution is wonderfully simple.
Yeah.
Take more vitamin D3.
Wait, just take a higher dose?
That's it.
Exactly. If you have a higher quantity of the vitamin flowing through your bloodstream, the sheer volume of molecules bouncing around means more of them will manage to force their way into those less effective, malformed receptors. By increasing the dose, you successfully trigger enough receptors to restore the normal, healthy, protective signal to the cell.
That is incredible.
Yeah.
But it raises a huge issue. If I go to my doctor for a standard annual physical and they draw my blood,
They will look at your blood work, check your vitamin D levels against the standard chart, and say, congratulations, your levels are perfectly normal.
right.
But they are looking at a chart designed for the average population.
Ugh.
Because of your specific, unique, defective VDR genes, your body actually requires a significantly higher concentration of vitamin D in your blood just to achieve the baseline protective health effects that someone else gets with a lower dose.
So I could have normal blood levels on paper, but my cells are silently starving for vitamin D because they can't absorb it properly. That completely upends how we view standard medical advice. Like, normal for the general population might be dangerously deficient for my DNA.
It really is the ultimate argument for precision health over one-size-fits-all medicine.
You know, if you're listening to this right now, hearing these massive percentages might have you mentally scanning your own family history or like wondering if your daily vitamins are actually doing anything. How do we ground this? What does this mean for the average person just going about their day?
The most grounding thing we can do is just look at the actual probabilities. Wallerstorfer breaks it down clearly. For those extreme genetic defects from the casino bucket, the high-risk genes associated with an 87% breast cancer risk and a 40% ovarian cancer risk, usually striking before age 45, the actual chance of inheriting that specific defect is only 1 in 370.
So that's about 0.26% of the population. So it's incredibly rare. If you have an average social circle of maybe 600 acquaintances, statistically only about 2 of those people carry it.
Right. So the immediate panic of, do I need to go get a massive genetic panel done right now, can be tempered. The book lays out very specific criteria for when you should actually seek out high-risk testing.
Let's run through those. Like, what are the red flags?
Essentially, you are looking for early onset cancers or rare combinations in your immediate family. Testing is recommended if a first-degree relative, like a parent or sibling, developed breast cancer before the age of 50. It's also recommended if they developed both breast and ovarian cancer or developed cancer in both breasts. And crucially, if a male relative developed breast cancer, that is a massive red flag.
And it extends to other types of cancer too, right?
Yeah.
Based on that family history shadow we talked about with Jolie.
Yes, absolutely. You should consider testing if a first-degree relative developed prostate, stomach, thyroid, pancreatic, or colorectal cancer. Furthermore, the test is advised if your family has multiple cases of breast cancer across different relatives, multiple cases of both breast and ovarian cancer, or if you are of Ashkenazi Jewish descent, as the mutation is more prevalent in that population. If you don't fit into those specific criteria, the high-risk genetic test is generally not necessary.
So we started this deep dive looking at the incredibly stark surgical reality of Angelina Jolie's high-risk genes, that casino bucket, the biological roulette that we can't negotiate with through diet or exercise. But where we end up is actually an incredibly empowering realization for the vast majority of us sitting in that lifestyle bucket. Finding out you have a genetic mutation doesn't automatically mean finding out you're doomed.
Far from it. It's really the shift from reacting to illness to actively engineering your wellness.
Yeah. Ultimately, understanding your genetic code isn't about predicting an unavoidable fate. It's about finally getting the personalized instruction manual for your own body. It tells you exactly what kind of biological support like. Maybe just needing a higher dose of vitamin D3 your unique system requires to thrive. Which leaves you to wonder, how many normal medical guidelines, from the vitamins we take to the diets we follow, will completely disappear once we realize our baseline health metrics are as entirely unique as our DNA? We started out talking about that comforting binary X-ray showing exactly where the bone is broken. But maybe the muddy waters of genetics aren't actually muddy at all. Maybe we've just spent our entire lives trying to read a deeply personal instruction manual using someone else's reading glasses.